20,000 years ago, ice covered a third of Earth's land surface. Glaciers 2 miles thick buried Chicago, while mammoths roamed where Manhattan stands today. Sea levels were 400 feet lower, allowing humans to walk from Asia to America. And then, in just 10,000 years, the ice melted away, forests returned, and civilization began. This planetary freeze has happened at least 5 times in the last 2.5 million years. Earth's climate is not stable. It swings wildly from hothouse to icehouse and back again. Ice ages lasting 100,000 years, separated by brief, warm periods lasting 10,000. We are living in one of those warm interludes right now. But the question remains, why? What forces make an entire planet freeze? And what triggers the ultimate thaw? The answer involves orbital mechanics, cosmic dust, ocean currents, carbon dioxide, and continents. Everything is connected, driven by subtle astronomical schedules that took centuries to decode. Welcome to Beyond Human Knowledge, where today we unravel the forces that nearly froze Earth forever. If you are fascinated by deep planetary history, please subscribe to support our work. Let us travel back 20,000 years to the peak of the last glacial maximum. North America was buried under ice from the Arctic Ocean down to present-day New York. The Laurentide ice sheet reached 2 kilometers thick over modern Toronto and Montreal. Its incomprehensible weight compressed Earth's crust, pushing the land down into the mantle. Today, the land is still slowly rebounding upward, recovering from weight that melted long ago. Europe was similarly crushed under the massive Fennoscandian ice sheet. Britain was connected to continental Europe by Doggerland, a vast dry plain inhabited by game. When the ice melted, sea levels rose 400 feet, drowning Doggerland beneath the North Sea. Southern continents also experienced expanding glaciers in Patagonia, Tasmania, and New Zealand. Yet, the giant ice sheets concentrated in the north, where vast continental land masses allowed ice to accumulate. Global temperatures were 5 degrees Celsius colder, dropping polar regions by 15 degrees. Forests vanished, replaced by the massive mammoth steppe stretching across Eurasia and North America. This cold, dry grassland supported giant megafauna, woolly mammoths, saber-toothed cats, and dire wolves. Homo sapiens survived along these frozen margins, using tailored furs, fire, and communal hunting tactics. Neanderthals, stocky and adapted to severe cold, had inhabited these ice age realms for millennia. Yet under climate stress and human competition, Neanderthals disappeared 30,000 years ago. The oceans were vastly different, with continental shelves exposed as dry, habitable land. The Persian Gulf was a lush river valley, and Beringia formed a dry bridge 1,000 kilometers wide. Human hunters crossed Beringia 15,000 years ago, entering the unpeopled American continents. The Ice Age climate was extraordinarily dry, locking water into glaciers and expanding global deserts. Fierce winds picked up exposed soil, creating planetary dust storms preserved today as thick loess deposits. Around 19,000 years ago, something shifted, and the vast ice sheets began to retreat. By 10,000 years ago, most megafauna went extinct as forests reclaimed the warming plains. This marked the end of the Pleistocene megafauna and the beginning of our current Holocene interglacial. Yet this was merely the most recent peak in a cycle repeating over and over. At least 5 major glaciations occurred in the last 450,000 years alone. For centuries, humanity failed to recognize the physical evidence left by ancient glaciers. Giant erratic boulders sitting in open fields were attributed to mythical floods or giants. In the early 19th century, geologists noticed parallel striation grooves carved into bedrock. These scratches, along with bulldozed moraine ridges and U-shaped valleys, pointed to massive moving ice. Swiss naturalist Louis Agassiz proposed the Ice Age theory in 1837, facing intense initial ridicule. Decades of field evidence eventually convinced scientists that continental glaciers were real. Early theories blamed solar dimming or volcanic ash, but none explained the strict cyclical timing. In the early 1900s, Serbian mathematician Milutin Milankovitch looked to orbital mechanics. He calculated 3 distinct orbital variations that alter solar radiation reaching high northern latitudes. First, eccentricity, the 100,000-year shift in Earth's orbit from circular to elliptical. Second, obliquity, the 41,000-year wobble of Earth's axial tilt between 22 and 24 degrees. Lower axial tilt produces cooler northern summers, preventing winter snow from melting. Third, precession, a 26,000-year rotational wobble dictating seasonal timing relative to the sun. Milankovitch proved that cool northern summers at 65 degrees north allow ice sheets to build. Though ignored during his lifetime, his mathematical calculations were proven decades after his death. In the 1960s, ocean drilling ships recovered deep-sea sediment cores containing microscopic shell archives. Foraminifera shells preserved oxygen isotope ratios, specifically oxygen-18 to oxygen-16. As lighter oxygen-16 evaporated and locked into land glaciers, oceans became enriched in oxygen-18. Analyzing these microscopic shells provided a continuous thermometer of ancient global ice volume. In 1976, spectral analysis confirmed that climate cycles match Milankovitch orbital frequencies precisely. Orbital variations act as the cosmic pacemaker, dictating the exact timing of global ice ages. Yet orbital forcing alone is small, requiring powerful planetary feedback loops to amplify the signal. The ice albedo feedback is immediate, as shiny white ice reflects solar heat back into space. Antarctic ice cores revealed that atmospheric carbon dioxide drops significantly during glacial freezes. During ice ages, CO2 fell to 180 parts per million, rising to 280 in interglacials. Orbital wobbles trigger initial temperature shifts, which cause oceans to release or absorb carbon dioxide. The ocean acts as a massive carbon sponge, sequestering CO2 in deep currents during cold periods. Dust storms delivering iron to glacial oceans fertilized phytoplankton, pumping additional carbon to the seafloor. Non-linear ice sheet dynamics created a dominant 100,000-year resonance over the last million years. Building massive ice sheets takes 90,000 years, while deglaciation collapses rapidly in 10,000. Before 1 million years ago, ice ages followed a simpler 41,000-year obliquity rhythm. The mid-Pleistocene transition shifted the planet into deeper, longer 100,000-year glacial cycles. Zooming out into deep time, Earth spent most of its 4.5 billion years in warm hothouse states. The Permo-Carboniferous glaciation 300 million years ago was triggered by the evolution of wood-building trees. Unrotted trees buried in coal swamps removed massive atmospheric carbon, cooling the planet into ice. The Ordovician glaciation, 450 million years ago, occurred as early land plants weathered rock. Extreme cryogeny and snowball Earth events, 700 million years ago, froze the planet from pole to pole. Equatorial glaciers and tropical dropstones prove that ice sealed every ocean under a kilometer-thick crust. Life clung to survival around deep hydrothermal smoker vents and thin equatorial meltwater pools. Volcanic CO2 outgassing accumulated over millions of years, eventually triggering a violent super greenhouse meltdown.
If we optimize the blade
34 million years
ago,
ago, the current icehouse epoch began as Antarctica froze at the South Pole. The uplift of the Himalayas and the closing of the Isthmus of Panama brought Earth to the brink of Pleistocene freezes. For 2.6 million years, humanity was forged inside this rhythmic orbital clockwork. Statistically, our current warm Holocene interglacial should be drawing toward its natural cold conclusion. Yet human industrial activity has added massive carbon dioxide, raising levels above 420 parts per million. Anthropogenic greenhouse warming has officially canceled the next scheduled orbital ice age. While delaying an ice age protects agriculture, rapid, unmanaged warming pushes the planet into uncharted territory. The deep geological archive proves that small climate nudges can cross rapid tipping points. Understanding our frozen past provides the vital key to navigating our planet's volatile climate future. Studying Earth's deep history reveals a fundamental truth. Climate does not change in smooth, linear paths. It is a complex, non-linear system governed by tipping points, feedback loops, and sudden, abrupt reorganizations. A tiny change in orbital tilt or atmospheric chemistry can trigger a massive planetary feedback cascade. The Snowball Earth episodes prove that once reflectivity thresholds are crossed, the entire planet can freeze solid. The rapid post-glacial meltdowns demonstrated that greenhouse gas buildup can vaporize ice sheets in millennia. The Younger Dryas cold snap showed that a single freshwater pulse can shut down ocean currents in a single decade. When scientists project 2 to 4 degrees of global warming, they describe changes equivalent to a glacial transition. These are not abstract numbers. They represent geological magnitudes backed by documented physical precedents. Understanding nonlinear climate dynamics is critical because human activity is pushing the planet toward new thresholds. Respecting planetary threshold boundaries marks the difference between civilizational stability and catastrophic disruption. Amidst these terrifying planetary convulsions, one overwhelming lesson shines through: the incredible resilience of life. Life survived a frozen ocean covering the entire globe, enduring conditions that should have been universally fatal. It persisted in pitch-black hydrothermal smoker vents, in subglacial lakes, and in thin equatorial meltwater pools. And every time the planet thawed, life did not merely recover, it exploded into unprecedented complexity. The cryogenian freeze birthed the Ediacaran multicellular forms, and the post-glacial world enabled the Cambrian explosion. The environmental crucible of the Pleistocene forged the problem-solving cognitive intelligence of our own species. The biosphere has survived 5 mass extinctions, global glaciations, supervolcanic eruptions, and asteroid impacts. Nature will endure whatever the current climate experiment produces, long after human civilization responds. Life is an unstoppable cosmic force, converting extreme environmental stress into evolutionary innovation over eons. The epic story of Earth's ice ages is ultimately not a tale of extinction, but of biological triumph. For 4.5 billion years, planetary climate was driven by geology, solar physics, and orbital mechanics. Today, for the first time, a biological species has become the dominant driver of global climate change. This new geological epoch is called the Anthropocene, the era where human activity reshapes the Earth. With this unprecedented power comes a profound, terrifying evolutionary responsibility. The brains forged by 2 million years of Ice Age volatility must now be deployed to preserve planetary stability. We are not separate from nature. We are its living, conscious remnants, carrying its ancient legacy forward. Understanding the deep geological past provides the vital map needed to navigate our climate future. The choices made in this century will echo through the geological record for tens of thousands of years. Humanity stands at the ultimate crossroads between stewardship of a living planet or catastrophic disruption. Look around at the modern landscape. Every valley, lake, and fertile soil carries the indelible mark of ice. The Great Lakes were carved by the Laurentide ice sheet, scouring deep basins into solid bedrock. The rich agricultural soils of the American Midwest and Europe are glacial loess wind-blown sediments. Our modern food production systems rely directly on the fertile legacy left behind by retreated glaciers. The Hudson River Canyon, Norwegian fjords, and Irish drumlins are physical monuments to glacial dynamics. Beneath our feet, the Earth's crust is still slowly rising in a process called isostatic rebound. Scandinavia and northern Canada rise millimeter by millimeter, adjusting to the loss of heavy ice sheets. The physical record of the ice ages is written into every rock strata, cliff face, and ocean sediment core. The planet remembers every freeze, every thaw, and every cosmic collision that reshaped its surface. We live upon the scars of an ice planet, enjoying a brief, beautiful moment of planetary warmth. A boiling molten furnace, a frozen snowball world, and 2 million years of rhythmic glacial volatility. The history of Earth reveals that our comfortable world was forged inside cosmic trials of extreme cold. The ice ages created the landscape, sculpted the biosphere, and selected for the human mind. Now, as we alter the atmospheric chemistry, we hold the steering wheel of planetary climate history. Which of these terrifying frozen transformations do you believe poses the most profound question to our future? Share your fascinating theories and insights in the comment section below and join the deep discussion. Be sure to subscribe to Beyond Human Knowledge right now for more deep dive classified historical documentaries. Click the notification bell to join our global circle of investigators before the algorithms bury these truths forever. Thank you for watching. Stay vigilant, keep questioning, and we will see you in the next deep void. Remember that the ground beneath your feet is always keeping score. Sleep well knowing the past is watching. Orbital mechanics operate on deterministic astronomical precision, predicting climate cycles centuries in advance. Rising sea levels could reshape modern coastlines, submerging low-lying regions across the globe. Ancient ice cores preserve exact samples of ancient atmospheres, trapped inside tiny air bubbles for eons. Greenhouse gases absorb outgoing infrared radiation, maintaining global warmth across interglacial epochs. The delicate balance between glacial cold and interglacial warmth defines the environmental limits of civilization. Woolly mammoths adapted to extreme Arctic conditions, developing thick fur and specialized fat reserves. Ocean circulation currents transport immense thermal energy, regulating climate conditions across continents. Early human ancestors crafted specialized stone tools, adapting to rapid environmental oscillations in Africa. Greenland's massive ice sheet holds vast freshwater reserves, sensitive to slight global temperature increases. Polar research stations provide crucial data, decoding planetary climate history buried deep beneath the ice. Volcanic outgassing releases massive carbon dioxide, acting as Earth's natural long-term thermal regulator. Variations in planetary eccentricity alter solar radiation, modulating seasonal contrasts over long timescales. Polar ice caps reflect solar energy back into space, reinforcing global cooling through high albedo reflectivity. Dust storms rich in mineral iron fertilize marine plankton, accelerating carbon sequestration in the deep ocean. Geologists decode the ancient past by analyzing rock strata, uncovering physical records of past planetary freezes. High mountain ranges influence atmospheric circulation patterns, creating regional microclimates conducive to ice growth. Earth's axial tilt controls seasonal intensity, influencing whether northern summer snow survives or melts. Submerged ocean caves contain ancient mineral deposits, preserving records of past sea level fluctuations. Ancient monuments align with astronomical cycles, reflecting early human awareness of cosmic rhythms. Extreme atmospheric events demonstrate the dynamic power inherent within Earth's complex climate system. Microscopic marine fossils record ancient ocean temperatures, providing a continuous archive of climate history. Geological maps trace the maximum extent of ancient glaciers, revealing how ice sheets reshaped continents. Northern lights illuminate polar skies, serving as a visual reminder of Earth's magnetic protection. Solar radiation drives the planetary water cycle, powering evaporation, precipitation, and ice accumulation. Lush, temperate forests expand during warm interglacials, replacing cold grassland tundra across high latitudes. Advanced satellite systems monitor global climate indicators, tracking real-time changes across the biosphere. Tailored leather clothing enabled prehistoric hunters to survive sub-zero temperatures during the last glacial maximum. Calving glaciers release massive icebergs into polar waters, contributing to global ocean circulation dynamics. Industrial human emissions have altered atmospheric carbon levels faster than natural geological carbon cycles. Tranquil natural landscapes reflect the long-term stability required for complex ecosystems to flourish. Prehistoric human bands utilized communal hunting strategies, coordinating efforts to take down megafaunal prey. The Atlantic conveyor current transports warm tropical waters north, moderating climate conditions across Europe. Winding river deltas deposit rich nutrient sediments, forming fertile agricultural regions across the globe. Tree ring growth patterns record past precipitation and temperature, providing yearly climate archives over centuries. Wind-blown dust deposits form thick, fertile loess layers, providing the foundation for modern global agriculture. Ancient stone architecture stands as physical evidence of human civilization developing during stable, warm periods. City lights illuminated from space highlight the global reach and technological capacity of modern humanity. Complex computer models simulate planetary climate feedbacks, projecting future scenarios under elevated greenhouse gases. Historical atlases document changing human knowledge, reflecting our evolving understanding of Earth's geography. Vast tundra expanses experience brief summer thaws, supporting specialized cold-adapted plant communities. Geothermal heat from Earth's interior drives volcanic activity, releasing gases that shape atmospheric composition. Polar research vessels navigate frozen polar seas, gathering critical data from Earth's most remote regions. Agricultural systems feed billions of people worldwide, relying directly on predictable climate stability. Fossilized plant remains reveal ancient climate conditions, indicating periods of intense warmth and severe cold. Interconnected climate feedback loops amplify subtle orbital nudges, transforming local shifts into global ice ages. Wilderness landscapes inspire human curiosity, driving scientific exploration into the deep mechanics of nature. Sunset fading over a frozen wilderness evokes the quiet serenity of a planet returning to peaceful equilibrium. Earth continues its cosmic journey through space, carrying the deep memory of ice ages past and future.